I was supposed to talk about binary lens and binary source events, but I generalized slightly to talk about multiple lens and multiple source events. Well, only binary source events, I guess. But the multiple lens, well, the binary lensing problem is part of the multiple lens problem, and so we're going to talk about it a little bit more generally. So the talk outline, I'm going to say one slide on binary sources, and I'm going to spend most of the time on binary lenses and multiple lenses, a little bit on binary lenses versus binary sources, and then I'll talk a little bit about some of the planetary events that were not easily identified by eye. All right. So binary source events are pretty easy, and they behave pretty much like you would expect. So here's a case where you have light curves of two different sources. So the two sources would be in orbit around each other to have any significant probability of both of them being lensed, and then you just add the light from the two together, and you get a light curve that looks like this, the sum of the two. The only complication, of course, is that stars don't have to have the same color, and if you observe in different pass bands, then you get different colors. Whereas with a single source, then microlensing events essentially look the same in every color. There's just a small difference between due to limb darkening. Yeah, and then also there is another effect where you don't actually need to see light from the companion to the source. You can see the effect of the orbital motion of the source, and that can give you occasionally can give you a light curve that you can confuse with a planetary signal. All right. So when we talk about multiple lensing, when we talk about lensing in general, there's sort of three planes we want to consider. There's the source plane, the lens plane, and the observer plane. Okay, and the one thing that we need to know from general relativity is the bending angle with light passing a massive body in a small angle approximation, and this is alpha equals 4 gm over c squared r. And so pretty much all the equations they're going to talk about can either be considered with all the coordinates in the lens plane, or somewhat more properly that these are angular positions. So they can apply to both the source plane and the lens plane. Okay. So the most straightforward thing is if you have perfect alignment, then by symmetry, if the lens is directly in front of the source, you get the Einstein ring. And this sort of sets the scale of the problem. And when you bring on the lens equation, we're going to normalize things to the Einstein ring. Also, the bright images are located close to the Einstein ring, and this is why microlensing is sensitive to planets at a few AU, because that's where, the distance of the Einstein ring at the typical separation of at the typical distance of the lenses toward the bulge. And I should mention that these figures are greatly exaggerated in general. The angular size of the source is generally much smaller. And when you get to high magnification events, the axis ratio of these elongated images is basically equal to the magnification. So if you have a magnification of 100, then one image is, due to a single lens, one image is magnified by a factor of 50.5. The other is magnified by 49.5, so the sum equals 100. And the width of the images shrink by a factor of 2. So at high magnification, the axis ratio of these images is the same as the magnification, basically. All right, so now here's here's the lens equation. So first I include all the constants before I factor them out. So there's three sets of coordinates here. W is the source position, Z is the image position, and then X are the positions of the lens masses. Okay, and so these, it's best to think of these as angular coordinates. It's all in the small angle approximation, so you could project them to the lens plane if you want. Okay, to simplify the equation, we're going to divide out by the Einstein radius. We'll use the angular Einstein radius given by this formula. And so when you do that, well, you not only divide out by the Einstein radius, you also convert from Cartesian coordinates to the complex plane. And this makes all the algebra much simpler. And so an equation for n-point masses is given by this. W equals Z minus the sum over all the masses. Epsilon sub I is the mass fraction. So the sum of one mass divided by the sum of all the masses in the lens system. And you sum that over all the lens systems. Okay. So to solve the lens equation, well, the simplest thing to do is to notice, we want to find Z as a function of W. But of course, if we wanted to find W as a function of Z, we already have the solution, right? Because there's no W's on the right-hand side. So if we know the image positions, then we can directly solve for the source position. Okay, and so a brute force way of doing this is to consider all possible image positions. Okay, so you basically shoot light rays backwards, okay, and then you work out which light rays hit the source. And this can be a bit computationally intensive because you may have to shoot a lot of light rays. And if you have a system in orbital motion, then you have to shoot a lot of light rays at each time you observe it. But it does have the advantage that it works for very complicated lens systems, including lens systems with, with an arbitrarily large number of masses or with continuous mass distributions. And so this is a method that is normally used for studying lensing by galaxies or clusters of galaxies where you have a more smooth mass distribution. And it's an important component of many of the methods we use to solve the lens equation. Okay, the standard way to solve for Z is to take that the lens equation and then take the complex conjugate of it. So and so then you can eliminate the complex conjugate between those two equations, and get another equation. Then you multiply through by the denominators, and this gives you a polynomial equation of order n squared plus 1. Okay, so for n equals 1, this polynomials are quadratic. You can solve it very straightforwardly analytically, and we've already discussed the solutions. For n equals 2, this is a fifth order polynomial with 3 or 5 solutions. Okay, well, the polynomial itself has, of course, always 5 solutions if it's a fifth order polynomial, since we're working in complex coordinates. So complex solutions are just as good as real solutions. But these manipulations up here have created new solutions. And so some of the solutions of the polynomial are not solutions of the lens equation. So once you solve the polynomial, then you plug your solutions back into the lens equation and determine which ones are real solutions and which ones are not solutions of the original lens equation. Okay, it gets a little more complicated when you go up to larger number of masses. For 3 masses, the polynomial is 10th order with 4, 6, 8, or 10 solutions. And you can work out the minimum and maximum number of solutions. The minimum number is actually fairly straightforward. You can actually understand the reason for this. And this is the minimum number of solutions is n plus 1. So it's n with one image associated with each source and one image associated with each lens. So there's multiple lenses in one source, and n plus 1. So if you consider the case where the alignment of the lens is not very good, then what you get is one solution for the source that basically goes straight to you without any deflection by the lens. And then the lenses are far from the line of sight. And so you get a single image from each lens where the image goes quite close to the lens, is bent by a sharp angle, and that gives it very small magnification. So you get a very tiny magnification image. And we'll see this in a video in a little bit. And that's a minimum number. You know, with one mass, you always got two images. Two masses, you got 3 or 5, and then the maximum number of images is a bit more complicated to work out. And in fact, no one was smart enough to figure out what the answer was. But there were 2 groups of people, or Sun Ri was smart enough to figure out half of the solution. She actually came up with a construction of solutions for any number of lenses that had 5n minus n solutions, and she conjectured that that was the solution to the problem. It turns out this problem is equivalent to a fundamental mathematics problem, an extension of the fundamental theorem of algebra. So the fundamental theorem of algebra involves a number of solutions to polynomial equations. This is involves the solutions to the equations that are inverses of polynomials. And Kavinson and Neumann are 2 mathematicians that showed that this was the upper limit, but they weren't sure it was the lowest possible upper limit. Neither Ri nor Kavinson and Neumann had any understanding of the methods used by the other, but combined they solved the problem. And it was only because there was some guy, a mathematician at UC San Diego, that read the gravitational lensing literature that anyone figured out that they had solved this problem. All right. To proceed with the solution, so 3rd and 4th order polynomial equations you can solve analytically, but 5th order you can't. But it's pretty straightforward to solve for solutions of a polynomial, 5th order polynomial numerically. And there's, standard numerical mathematics packages have programs to do this. In general, you want to use double precision if you're considering planetary events, because sometimes there's a lot of cancellations in these polynomials. And for triple lens cases, you sometimes need quadruple precision, which actually is the reason that it makes things easier to do in Fortran, because many more Fortran implementations have extended precision than other programming languages. So some of us old fogies have an excuse to continue using Fortran. And then once you solve for the solutions, of course, you have to plug those values back in to see if they're solutions of the original lens equation. Okay, so this is how you find the locations of the solution, locations of the images for lenses are made up of point masses. But this doesn't directly give you the magnification. But lensing doesn't affect the surface brightness. And so for any point image you have, then you can just assume that it has the same surface brightness on the source. And so if your source is a star, then the surface brightness is the same up to limb darkening. So you just need a limb darkening profile to tell you what the brightness would be on any area element of a lensing event. Okay, and if you assume that the source is very small, then you can work out the magnification from the lens equation. Basically, it comes from the Jacobian determinant of W with respect to Z, or 2-dimensional. Since these are complex coordinates, there's W and Z both have 2 dimensions, the W and the complex conjugate. And so this is a ratio of the magnifications. Since the derivative with respect to the image, not to the source, then the magnification is 1 over the Jacobian determinant of the lens equation. Okay, and So as was mentioned earlier, a crucial feature here is the caustics, and we know that the magnification of a point source at a caustic is infinite. Okay, and so this means then that the Jacobian determinant is 0, and so the magnification is 1 over that. And so basically, the critical curves are defined as image locations where the Jacobian determinant is 0. And then the caustics are the corresponding source locations. So you calculate the critical curves by setting Jacobian determinant equal to 0, and then you plug that plug those image locations into the lens equation to determine where the caustics are. All right. So as Scott mentioned, what we're doing is a mapping between two-dimensional surfaces. The source plane, what you would see if there was no lens, and the image plane is what you actually see. Okay, and this is a smooth mapping, and you can imagine it's a mapping between say a flat plane like the floor and a flat plane like the floor and then an elastic sheet that's distorted by the gravitational lensing, but it's still continuous. Okay, so you imagine you have some sheet that's deformed in some way and maybe multi-valued. Well, and just project it straight down to the floor to make the mapping between the image plane and the lens plane and the source plane. So here you have a case where that mapping is just 1-to-1. You have some distortion of the area of the source compared to the image, but there's one image for that source. And then over here is a case where you've got a 3-to-1 mapping. Okay, and so immediately you see why you have to increase the number of images by 2, because if you're just doing a smooth mapping between these two surfaces, you can't add an odd number of images. And then, of course, when you go from one to the other, you see that the new images have to be created together, merged together, and also they're created at a tangent point of this mapping. And so this is why for an infinitesimal source, infinitesimal source will correspond to a finite size here, and that's why it's, or a larger size anyway. The ratio of the image size to the source size will be infinite at this tangent point. That's why you get infinite magnification. And so this is a generic thing of mapping to two-dimensional surfaces to two-dimensional surfaces. And if you ever look at the bottom of a swimming pool on a sunny day, you can see lots of caustics from the imaging due to the waves on top of the water, then making mappings like this where you get multiple images that can give you bright spots on the bottom of the pool. Right, so what we're seeing here is when the video starts off, we see the blue Einstein ring, and then we focus in on the major image caustic, and then so here's the Einstein ring. Here's a major image caustic. Okay, and so we focus in on that, and then the planet is coming up here near this other image, and then it moves across here, and you can see kind of a circulation of the features going across the Einstein ring. Yeah, so this is actually the light curve of the event, and so when we focus in, we're seeing this part here, and this is a comparison of the caustic size to the size of the source star, and that's why we basically see only one image, because the multiple images are only the multiple images are only on part of the star, and so all the images are merged together. All right, so this is the same video we just saw, and then once again here's the image next to the planet, and then we get this Einstein ring. You can see all this rotation here. That's the image of the part of the star that's right at the Einstein ring. All right, this is a close-up. Okay, so here's where the planet is. You can see all that fast rotation. It's the same kind of thing you saw in some of those LIGO videos where you see the background objects and you get this very fast rotation. And you also see that, the planet is located right here. This is that image that starts out very close to the planet when the alignment is bad. And there you see that once again. All right, so here's now just a comparison when we consider a case that's the same, except that we increase the mass of the planet by a factor of 3. And you see that basically the thing that's changing is the angle of deflection around the planet. That's just what the mass does. And so, but you can also probably tell that, when the planet is right in the middle of that image, that the total area of this image on the right is significantly larger than the image on the left because of that basically larger bending angle. And here you get like a 45% effect, and here it's something like 15%. All right. Okay, so as Scott mentioned, this is a magnification pattern for this particular event, and here's where the caustics are. And so, as Scott mentioned, the magnification is associated with the caustics. And the features that give infinite magnification are the caustics and the cusps. All right, and this just shows how they behave when you go across a Kostik crossing. So here, it's plotting separate images. So there's 3 different lines for 3 different images. I guess this dotted line is actually the sum of the rest of the images. And so you see 2 of the images get very bright and then they disappear, right? So those are the 2 extra images. And that's shown here. You get these 2 images that are forming right on the critical curve and then moving away after the Kostik crossing. Or I guess in this case, maybe you're exiting the Kostik, so they're moving towards and annihilating at the Kostik crossing. And then and then these are like finite source effects for those 2 images. And if you have a larger source, you get a longer time scale. But you get these characteristic features of limb darkened source crossing the Kostik. All right, so the cusp situation is a little bit different. This is now magnification contours at the location of a cusp. So this dotted line shows where the cusp is. And so these are 3 magnified images, but 2 of them annihilate. And so they have very high magnification along the Kostik, but then they disappear outside the Kostik. Whereas the other bright image then has this magnification extending outward from the cusp. And this is very much like the magnification due to a single lens event, as Scott mentioned. All right, and I think Scott showed this as well. This is the wide, close, and intermediate caustic. So I'll go over this pretty quickly. For equal mass lenses at separation of 2, then you have this case where we have 2 outer caustics of just splitting between 1 caustic with 6 cusps and 2 caustics with 4 cusps each. Then at a separation of 1 over the square root of 2, you have this central caustic splitting up into 3, 2 triangular caustics and 1 with 4 cusps in the middle. All right, and so in a binary lens case, you just have one, basically you can be either inside or outside of the caustic. You can't pass multiple caustics, but that's not true with higher number of lensing events. And so here's a case, triple lens case, where you've got 4, 6, 8, or 10 images. So if you start out here, you start with 4, then cross a caustic 6, another caustic 8, and to the center here you get 10. And in here with 4 lenses, you've got from between 5 and 15 images. In general, we don't expect to see configurations like this. These are very symmetric. That allows for easy solutions to the lens equations. With multiple lenses, we tend to have different separations or a large ratio of masses. But nevertheless, we do expect to, certainly with W first, to see some situations where you see a Kostik crossing and then another Kostik crossing, even more images before you get an exit. And I think we have at least one example of that observed from the ground. I think Scott showed this as well. This is a relative magnification divided by the single lens for the planetary case for wide separation, close separation, and this intermediate Kostik. So yeah, here's the major image Kostik again. And as Scott mentioned, there's the deviations here are primarily positive, but you have some negative deviations away from the cusp, just outside the Kostik. But the minor image Kostik is different, and in fact, this magnification deficit feature in between the two triangular Kostiks is pretty important, and for the smallest mass planets, it can sometimes give the largest signal. This is a case of that one event that Scott showed. Let's see, and yeah, here's the light curve, and then basically, when you basically destroy the lower magnification of the two images with a magnification of about 2.5, and so the magnification drops from about 6 down to about 3.5 when this image is destroyed, and then you hit this other Kostik and go back up to around 6 again. Okay, so this shows what happens with finite source effects. So here's the same light curve then calculated with several different source sizes. So here's one with a separation of 0.8 times Einstein radius, and here's one with a separation of 1.3 times Einstein radius. And what happens when this, with these minor image Kostiks, if the source gets too big, then that negative magnification region in between the two triangular Kostiks can basically completely cancel the positive deviation from the Kostiks themselves. And so when you have a big source crossing them, you just get no deviation at all. And so this goes completely smooth. Whereas in this case, where you have the major image perturbation, the large source saw just spreads out the deviation over a larger area. So the size of the deviation drops because the source spreads it out over a larger area, but the deviation doesn't go away. And so it's potentially possible to measure deviations here in this situation. The only problem is that the giant source stars also tend to be a little bit more variable, and so if your deviation is getting down below 1%, you have to worry about stellar variability interfering with your measurement of it. Okay, so of course we're not. This is a magnification pattern for a magnification map for an event with a fairly massive planet. But of course, we're not measuring magnification maps. We're just looking at the case where a single source crosses the magnification pattern, and so this happens a lot. Oftentimes. Okay, so as I was saying, oftentimes we're unlucky, and there'll be a planet there that could give a nice signal, but the source star heads in the wrong location, and all we see is the signal from the star. This is why we have to observe lots of microlensing events, particularly in the surveys, to get a good sample of planets to compute statistics. Of course, other times, we cross the planetary Kostik, and as Scott mentioned, the planetary Kostiks are generally bigger. So as long as you're doing good photometry, when the source isn't magnified by very much, you have a higher probability of detecting the signal here. And then the other type of well, another type of event is the one with a central Kostik perturbation. And this has the advantage that it occurs at high magnification. And so you can predict ahead of time that you're going to have high sensitivity, which, this is why we tend to focus on high magnification events when we have choices for our observing. And of course, the high magnification also allows smaller telescopes to be useful. All right, so here's an example just showing the differences between the different Kostiks for one of these resonant Kostik events. So here's the light curve, and there's 4 different Kostik crossings. Okay, so the first Kostik crossing occurs here, and this was an event we were monitoring in real time, and it was high magnification, so we were getting a lot more observatories involved. And when we saw this feature, pretty much everyone assumed that this was photometric noise. And it was only after we got the other features that saw that it had to be real. So this very weak feature here, this corresponds to this Kostik crossing here. And these outer Kostiks are fairly weak, particularly in the resident Kostik case. Then it hits a Kostik B, and this is crossing into the region behind this sort of central part. And this is a very strong Kostik, and then you get increasing magnification here. This is from basically the single lens effect. But one of the images is basically destroyed in this area. And so it's just a major image that's getting magnified. Then we hit this Kostik crossing here that's really bright, gives you a huge signal. And then here, this Kostik crossing is basically pretty much invisible because it's so weak. And basically what's happening here is that you've got a long ribbon image, and the Kostik is just affecting a part of the image. All right, so I want to say a little bit about numerical methods here. Valeria is going to talk a little bit more about this. To do calculations with finite source size, which you generally have to do when you have Kostiks because the sources are all finite. There's a sort of semi-analytical way to do, you can do a hexadecapole approximation or a quadrupole approximation that improves on the single lens, on the point source calculations. But it's not very general. It doesn't work for Kostik crossings. So it helps to speed up the code for some events, but it's not general. There's a brute force ray shooting, which has the advantage that you can use it for very complicated systems, but it can be very slow. There's a Stokes or Green's theorem approach. Dominic Gould and Gaucherel and Valerio has the most advanced implementation of this. He's going to talk about this. This is particularly fast for uniform sources. And probably competitive for realistic limb darkening. It's a little more tricky to implement it for more than 2 lens masses, and I don't think they have a working version yet, although Valerio is optimistic. And then this direct integration of the point source formula over the source plane, this is integrating over the Kostiks themselves, where they're highly singular. And this, this has only been tried once by Greist, and it didn't work out very well, so I don't think anyone else is going to do it. And then the method that I use is this image-centered ray shooting. And so basically, we solve the single lens equation, find the locations of the sources, and then start building integration grids at the location of the sources. And we also have to identify any Kostik crossings to make sure that we build image grids there. This is pretty flexible, and it works pretty, we got it to work pretty well for triple lenses. Should work as well for quadruple lenses. It's very useful to use polar coordinates. And I think currently it's the only practical method for fast orbiting triple lens systems. So we used it for this this circumbinary planet event that we published last year. So this is why you want to use polar coordinates. Is these highly magnified images get bent into very long arcs, often with an axis ratio much larger than this, more like 100 to 1. And if you use a rectilinear grid, then you're finding out that you're calculating on all these grid points where there's no source, so you're doing calculations for nothing. Plus, everything's elongated along the region, along the arc, it's better to use, to use polar coordinates, and then you can have many more grid points in the radial direction than in the angular direction, so you use many fewer points. And another thing that few people worry about, but this can make a big difference in calculations for high magnification events, is that the standard limb darkening profile is a singular derivative at the limb. And this is true for sort of standard square root model formulas that come from, say, the gray atmosphere. But it's also true for any other atmospheric model. It's just what you get for a semi-transparent atmosphere and spherical geometry. So you always get some kind of 1 over square root divergence, you get this 1 over square root divergence at the limb in the derivative. And so this means that standard second order integration schemes aren't going to work. So I've developed a method that actually takes that into account and does second order integrations, and this speeds up the calculations by more than a factor of 10 for high magnification events. High magnification events, this is most important because these have these long skinny images that have a huge ratio of boundary of limb to area to area. All right. Okay, so I'm supposed to talk about binary lens versus binary source. So Gaudy wrote a paper in '98 arguing that this was a possible astrophysical false positive. And here's generally most of the planetary microlensing light curves don't resemble ones that can be mimicked by a binary source. But the first low mass one, Ogle 05 390, did, and here we fit for that. And then this year we published a discovery paper for Ogle 16 1195, and here we fit a binary source for it. And basically the difference is here in the wings of the image. The planetary light curves have a much sharper drop off in the wings and either come down below the point source model or come very close to it. And in here, so it's the same thing in both these cases rules out the binary source models. Okay, so here's a case where you have a planetary model for this event that well, you have a planetary model and also a binary source model, but there's something rather strange about a couple things strange about the planetary model. First of all, the source is going almost directly down the lens axis. So that's a little bit unlikely, but of course, it does give us more chance to detect the planetary signal, so maybe there's some bias in favor of it. And then here, this is just a close-up of this best fit planetary model here in black. And it shows that basically we're required to have a fairly large angular source size to smooth out all the sharp features in the light curve. All right, and in fact, it doesn't completely smooth out all those features. So that's an indication that there's something wrong with this model. In fact, the binary source model is correct. All right, here's another one that's even older and not published. This is one that we worked on for a long time as a possible planetary model. It looks like it's coming in on the back side of a central caustic or a resonant caustic, and then this magnification could be related to the front end of the caustic pointing out. But here, this is actually a triple lens model, which fits a lot better than the binary lens model. But here we have these sharp features that are not reproduced in the data. And this is actually an example of a binary source model where there's only one of the sources is bright. 5 minutes. 5 minutes. Yeah. And so, yeah, so this one, basically all these features are coming from the orbital motion of the binary at a fairly short period, period of order, I don't know, 5 days or something. But because it's a high magnification event, that can give it very, very good alignment for a short period of time. And once again, the hint here is that you've got something generically that looks like a planetary model, but all the models have sharp features and the data doesn't. So that suggests that it's not a planetary model. All right, so here's the one event with binary source and a planet. And this one was a bit of a puzzle in the beginning because people looking at the light curve by eye said, oh, this looks like a classic case of crossing the two minor image caustics. But people modeling it found that model did very poorly. Basically the models look like this. They couldn't reproduce the brightness here. The models wanted to basically kill that minor image and drop the brightness more. And in fact, this model is unphysical because it requires a source star to be brighter than the stars you see in the sky at that location. And so there's two possibilities. There's something else adding extra light to what's a normal sort of planetary model. And at first, the thing that seemed to work the best was a circumbinary planet, where instead of these caustics, you also have the planet is orbiting a binary star system, and that's causing, generates this caustic, but then because of the orbital motion, it's rotating. Okay, but there's suspicious things about this. First of all, it's rotating at exactly the same speed that the source is moving. Okay, and that's what keeps the magnification relatively flat here. Well, that's pretty suspicious. The cusp pointing in this general direction. It's not pointing directly at the source, but it's maintaining the same angle. So that's unlikely. Normally with a cusp there, you would see some sort of bump. And then the other thing is that the orbital motion is really too fast for the two stars to be bound at the separation they're at. So the correct model turns out to be one with a binary source. There's basically two sources. The one that sees the planet is a little bit brighter, but they're both going on opposite sides of the lens system. So one of them sees the planet, the other one doesn't, and that basically fills in the magnification. At the bottom here, we get slightly different magnifications for the different passbands. All right. So then I got a handful of these events that were difficult to find in initial inspection. Here's one with a very high magnification event that had a very subtle Kostik crossing feature. The groups that got data on this didn't recognize it as a planet, but Nick Rattenbury of the MOA collaboration did, and eventually this turned out to be correct. This is actually the only planetary signal that's been confirmed by follow-up observations, because we predict the separation velocity of the lens and source from this feature, and we measured that a few years back with both HST and Keck. This is one that Scott showed. Here, if you just look at this, you don't see the planetary signal. This is because the size of the source is larger than the caustic, and so you just get little features here of a few percent. This is one that remained unidentified as a planetary signal for 3 years. And this is, the light curve looked like this. And basically, when people looked at the light curve, they thought it doesn't look like a normal lensing event. But actually, it is a normal lensing event. It's just that the source is very faint and it's a high magnification event. So all we're seeing is a high magnification peak. Okay, and this is what the caustic configuration looks like. So the source crosses the caustic down here. Then it exits this caustic here, crosses in front of that cusp, and then hits this caustic as well. So this one took 3 years to identify. This one was a little bit similar. It's not quite as high magnification. This took 3.5 years to identify. But here it also has a very large signal crossing the strong caustic, giving a very strong caustic here. And people assumed that this was a stellar binary lensing event without modeling it until we had a systematic modeling effort. All right, finally, we have this one, which suggests that there's other events that are being missing. So this one is a planet in a binary system published by Gould et al. And so you see there's this dip in the light curve. And this was seen both in MOA and Ogle on the rise. So this was pretty clearly a planetary signal. So we had an event that was heading for high magnification after we already saw a planetary signal. And then we were very surprised to see this giant signal due to crossing of a stellar binary caustic. So it's a planet in a stellar binary system. Okay, but as a part of the analysis, Gould et al. Also tried modeling this event, throwing out the data around this time, so throwing out this dip. And they found that the planet was still needed to fit the data. Okay, and in fact, if you look at this, if you consider all the events that are crossing this central caustic here, how many of them are going to cross this feature as well? It's a pretty small fraction. And so you would guess that there would be something like an order of magnitude more events where you could detect the planet based on the feature of a binary lens caustic without a separate planetary signal. But to date, we haven't found any of those. And this is probably because our systematic modeling methods so far aren't really sophisticated enough to do that. But we're planning to try and attack this more systematically. And we might find a lot more planets and binary events in our that we already have. And then this is the one that Scott showed where we don't have the solution yet. So I can talk about this if someone asks some questions, but otherwise I'm done. Sure. Yeah, so this was an event, a high magnification event with like a very, very faint source. It's a little challenging. So some of the critical data here is from amateur telescopes. This is data from SAO, so a larger telescope. This is amateur data. Here's Ogle data. So it's got a lot of fragmentary light curves, and this makes it a bit of a challenge, in part because it's a little bit hard to identify systematic errors when you just have a few data points. But nevertheless, we did some modeling of this, and the first model I did predicted a Kostik crossing out here. And we circulated it to various of the groups, and Andrei Udalski went off and found another observation here. And in fact, that observation was a lot brighter than, so this is one that hadn't made it into his original light curve. And so that provided, some evidence that maybe something like this model is correct. And this is basically this model with orbital motion, and this is the source entering the caustic around here. Okay, and so then it takes a long time to go through here, but then it reaches high magnification. This is I think this is, I can't remember. I think this is a two-planet model. The features up here are due to the other planet, and then you have this caustic exit. Okay, but the strange thing about the caustic exit here is at an extremely shallow angle at about 5 degrees. It's almost parallel to the caustic. But the timing of the caustic crossing is normal, like you would expect. The normal time it would take a star to cross its own radius. Okay, so, but of course, because of this tangent, then the source radius crossing time has to be about 20 times shorter than the actual feature in the light curve, right? So that implies that the source is crossing extremely quickly, and then applies a very large angular Einstein radius. And so if this model were correct, then the lens would have to be a 2 solar mass star. There's also this data point that doesn't fit, which fits some other models that have a caustic crossing there. And so, we think there might be something right about this model, but this caustic crossing feature at the very shallow angle seems likely to be incorrect. And I think what the main problem here is that that we can't solve this like we have solved most of the triple lens events, where we fit a simplified model with including 2 masses and then do a perturbation on that to add the other mass, or we see events like the one Scott talked about with very clear features for each of the planets, and you can identify by eye what sort of model you might want. Here the data are kind of sparse. We have to do a brute force search with probably a much larger set of parameters, and that of course takes when you increase the dimensions of your parameter search, that increases computation speed by a lot.
Sorry, we are really over time, and I really want to leave some time for coffee because then we need to come back for the hands-on and eating time.